for you, for those who never study about material science. Okay, so this topic is aimed to let you understand why alloying element is added into horse metal, and you should be able to understand the concept of a solid solution and solubility limits, understand what is phase diagram and how it is being constructed. Okay, so as an introduction, many pure metals are too soft for general use. Okay, they can be made harder by adding another element to the pure metal. Okay, and it will produce alloy. Remember, in previous two chapter, module 3 and module 3 and module 4. Okay, we study about the strengthening mechanism, and one of the method to strengthen our materials by using alloying. Okay, we induce um, uh, foreign element to the parent elements to make it harder or stronger. An alloy is a materials that is made up of at least two different chemical elements, okay, one of which is a metal. So when we talk about alloy, there are two different mechanisms that will produce the alloy. Okay, one mechanism through the substitutional alloy, and another we call it interstitial alloy. By the name, you can guess what is the mechanism that allow the foreign element to combine with the parent element to become an alloy. So when a molten materials, okay, meaning that during in the liquid form, is mixed with another element, there are two mechanisms that can cause an alloy to form. Okay, one we call it substitutional, another one interstitial mechanism. Okay. So again, you have learned about this interstitial and substitutional in the chapter 3, which is during the diffusion, during the solidification, during the we discuss about the defects, okay, at the atomic level. So this is actually defects. These are the defects. Okay, this is combination process mechanism to form an alloy. Okay, one is alloying element having large size compared to another alloying elements. This one can produce interstitial, and these large elements, foreign element, can produce substitutional alloy. Okay, so from one chapter to another chapter, it is interrelated. That's why you have to learn at the earlier part compared to another topic. Okay, so now we are coming to the making an alloy. All right, making an alloy. So when we talk about interstitial alloy, for this kind of alloy, the component present in the interstitial position between the solvent atoms between the step must have a much smaller. Okay, we have discussed about this in the last topic. Okay, if the alloying elements or the foreign atom having very small size, so it can produce alloy through the interstitial diffusion. Okay, this is example. Iron as the parent atoms or the host materials, and the carbon, which is very small elements, it diffuse. Okay, this is not the original size of atom. This is just a position of atom. Imagine this is the center of the atom. Okay, atoms of non-host metal, we call it solute. Okay, it's we replace host atoms, which is solvent, in crystal lattice. Okay, when it's involved taking the original place or position of the original materials, it's always substitutional. Okay, the mechanism is substitute. Okay, it replacing the original position that belongs to the parent atoms. Okay, for example, bronze. Okay, bronze. Look at this color. Okay, there are two different color. One is copper light color. Another one is silver light color. So when they forming an alloy, you can see that it is almost identical in size. Okay, copper is a host, and the tin, okay, is a alloying elements. Okay, it will fill up the vacancy that leave by the parent atoms. A solid solution is a solid state solution. Okay, it's a solution. Okay, solution, right? When we mix something, there is a solvent, and you put something inside the solvent, it will become solution. But when we talk about solution, solid solution is the same concept with a liquid, but this one is in the solid form. Okay, so if you are making a syrup, you put a syrup inside, or for example, you put a sugar in the water. This is sugar, and this is water. So you will have a syrup, a solution of water containing sugar, and this is in a small amount. This is a major constituent. Okay, so if you have a molten materials, okay, this is metal in the liquid. Okay, you add 10% of alloying element, and this combination will solidify and forming a solid. So in the form of solid, also we call it solution. Okay, but we name it as solid solution. Okay, a multi-component system is considered a solution when the crystal structure of the solvent, remember this, crystal structure of the solvent remains unchanged by addition of the solute. Okay, for example, if we have the steel, iron, okay, we add carbon. When we add carbon, this iron having BCC structure, we add carbon, it doesn't change the original BCC structure. So, okay, then it's a still maintain a solution condition. Also, the solvent chemical component remain in a single homogeneous phase. But when you try to soluble some, when the alloying elements try to dissolve in the solvent, okay, there are some limits. Okay, you cannot add, for example, if you making sugar water, okay, you cannot add sugar until 100% sugar. Okay, for example, you have water, okay, you add sugar, okay, you will form a syrup or sugar water. Okay, you can dissolve it, but after some limits, you can see there are a crystal of sugar that remain undissolved. Okay, meaning what does it mean? Meaning that you have a limit of the amount of sugar into the water. Okay, so the limit where the limit of the solubility of sugar in the water. Okay, this limit is the maximum concentration of for which only a single phase solution occurs. So what is single phase? In this case, the sugar water, the single phase. Okay, if you add more sugar beyond this limit, okay, beyond this limit, what you get is the sugar itself and the sugar water, okay, the syrup. So that's what meant by the limit. Okay, maximum concentration for which only one single phase solution occur. So beyond the limit, you will obtain two phases. Okay, so it actually depends on the temperature and the concentration. Okay. Okay, for example, in the lower temperature or maybe room temperature at this level, this is the limit of sugar that you can add in terms of the percentage. For example, this is 60% of sugar that you can dissolve in the water. But if you heat to 100 degrees Celsius, maybe you can have more, okay, more sugar inside the water. Okay, so this limit actually depends on the concentration and the temperature. Actually, in the WhatsApp group, I already shared with you the lecture notes. Okay. All right. Type of alloy. There are several types of alloy. One of them is number one, a complete solubility limit alloy. Okay, meaning that there's the limits is it can be dissolved completely. Okay. Another type is you can dissolve until a certain amount, partially, 100% soluble, and beyond that limits, you won't be able to obtain that the first or a single phase. Okay, a mixture of pure crystal, or we call it insoluble. You try to mix the two elements, it doesn't form any new elements. Okay, for example, when we add sugar and water, what you get if you add sugar and water? What is new phase? Okay, originally we have phase sugar plus phase water. There are two phases, right? So when you add this, what is new phase that may obtain?
Water.
Water. Kalau you campur gula dengan water, jadi water.
Air gula.
Air
Sugar
gula.
water.
Sugar water. So that sugar water is a new phase. It's a alloy. Okay. Of course not alloy. Alloy we refer to metal. But this is what meant by producing alloy, soluble alloy. However, this kind of alloy is soluble. You don't obtain new phases. The pure metal, for example, metal, metal or elements. Elements A plus elements B. Okay, you can mix it. You can mix it. They can sit together, but they don't form any new phases like sugar water, like this one, or syrup. Okay, like this one. No, they cannot form it. They are completely insoluble. Okay, they can sit together. They can form new materials, but they did not form any new elements, new phases. Okay, for this one, you can add A plus B as much with no limits. Okay, you can add B into A, start from 0%, 1%, until 99.99%. Okay, you can mix it. That forming only one phase, no other phases. Means that there's no limit. So complete solubility limit. Okay, completely. You can. There's no lines like a sugar and water. Okay, a complete solid solubility alloy gives a single solid phase. See, single solid phase microstructure. Complete visibility of the host element and alloying element in both molten metals and crystal phase. Tak ada dia. Sorry lah, bilik saya ni ramai orang tengah betulkan aircon. Kalau tak dengar banyak sangat noise background, bagi tahu lah. You all yang senyap je kan. Senyap je, saya assume you all okay lah. Alright. So when you try to add mix these two elements, complete solubility limits type of alloy is forming only single solid phase. Okay. So you can see it is uniformly mixed, and this one is grain boundary, just a normal like a pure metal. Only one single phase. Okay, like pure metal, aluminium pure, you can see only one single felt, which is aluminium. And for this kind of alloy, so similar like that. For example, the red elements forming a pure metal is contain all red elements. For B, alloying element is for pure metal is only one blue atoms, but which is one phase. But for this complete solubility, all containing A and B, okay, red and blue, okay, it's the same composition, not the same composition. I mean that same phase. Okay. So the system for this type of alloy remains in equilibrium throughout its history, so that all reaction can take place and everything can come to stability. Okay, is remain the crystal structure. It still means remain as its original crystal structure, the electronegativity and everything. Okay, everything in the original maps remain in a communication throughout the crystallization process. Ions of two different elements can freely replace by another only if they satisfy Hume rotary rules. Okay,
Hello, Teh.
yes.
Nak tanya yang apa maksud dia, the system remains in equilibrium.
Equilibrium means that macam mana contoh saya beri contoh je. Okay, for the alloy, when let me give some example for that. Okay, later I will get to you what is the most appropriate example to explain this equilibrium condition. Okay, for example, the ionic condition, the valence condition, and I'll give you some example later. Okay, I'll get back to you. Mean equilibrium is not active, active to the environment, something like that. Okay. So this is example copper nickel. Copper nickel is one example for the complete solubility limits alloy. Okay, copper and nickel. Why? Because it satisfies Hume rotary rules. What is Hume rotary rules? Okay, you have learned this in the chapter chapter 3 for solidification that allows substitutional diffusion. Okay, substitutional. You can go back in the chapter 3 where number 1, the size difference is the difference in terms of the radius for the atom is less than 15%. Number 2, electronegativity is identical electronegativity. Okay, the valence identical, almost similar, and crystal structure. Okay, either it is FCC or BCC. Okay, for copper nickel, both have FCC and BCC. The size is almost same. The electronegativity is almost same, about 1.9. The valence is similar, +2. Okay, the valence of electron valence similar. So that's the reason this kind of combination can produce complete solubility limits of a lot. Okay, partial is similar with the sugar plus water. Okay, beyond that limits, you will produce more than one phase. Okay, if the sizes of ion is close enough, but higher than 50%, higher than, okay, just now when we talk about Hume rotary, okay, the size, the different size is less than 15% between element A and B. Okay, but for this one is higher than 50%. The substitution may only occur over a limit range of composition, and the solution series is said to be partial or limited. Okay, so there's no homogeneous that you can see. There are two phases. One, this is phase A. This is phase B. Okay, phase A, you can see more red elements. Phase B, you can see more blue elements. Okay, they are not identical. They are not homogeneous. Okay, one is more element blue. Another one is more, the solvent is element A. Okay. So, okay, in this case example, the blue is alloying elements, but the red is host element, the parent atoms. However, due to the formation of different phases, another phases is what you can see, the concentration of alloying element is more on this region. Okay.
Oh, balik rumah tu ada sister ke?
So, in the system for the okay, for the phase diagram system, okay, solid solution they label sometimes, okay, it depends on the alloy system. Okay, the phases they label as alpha, beta, gamma, something like that. Okay. Right. For example, the lead, plumbum, and tin. Okay. The lead having FCC, and the tin has VCT. Okay, they are identical in terms of the crystal structure. So the alloy that form is not complete solubility, but instead partial or limited solid solubility. So in this region, okay, for the lead tin alloy or iron plumbum tin or plumbum standard alloy, for the alpha, it contains plumbum bridge, meaning that the major element is plumbum. Okay, and for the oh sorry, okay, there are two, okay, forget about the early explanation. Okay, you can differentiate between these two phase. Okay, one is alpha, one is beta in terms of the contrast color that observed from this microstructure image. Okay, as you can see, this is a white color. This one is a black. They are actually contrast because they respond to the light or the electron from the microscope differently because of the behavior of the atoms, the density of the atoms. So, for example, here the dark color, we call it phase alpha. And in this dark color or alpha phase, it is plumbum bridge. And for the beta, okay, it is a lighter color, and the concentration of stannum or tin is higher at the lighter or brighter phase. Okay. So when host elements and alloying element have a different lattice structure or has a very different chemical properties, they probably not be able to form solid solution at all. Okay, we are talking about solid solution. We are not talking about they cannot form alloy at all. They still can forming an alloy, but there's no solid solution. Dia tak ada larutan gula tu. Air gula tu tak ada. Okay, sugar water is not formed. Of course, it doesn't involve sugar and water, but it's something like this. Okay. So when you mix, okay, this is only elements A, this is only elements B. Okay, they don't mix. Okay, you can see they sit together next next to each other, but this atom is not diffused to this atom. Okay, so we call it insoluble. Okay, very simple example. Kalau you campurkan minyak dengan air, dia larut tak? Is there any possible to form a new phase when you mix between oil and water?
No.
No, doctor.
Oh.
Can we mix oil and water?
No.
No.
Yes, we can mix, but they don't form any new phase.
Yes.
Okay. Betul tak? We can mix oil and water, but they did not form any soluble. Okay. So completely insolubility. Okay. The atoms of oil cannot diffuse into the atoms of water. So example, okay, this is the real alloy that we produce. It is bismuth and cadmium. Okay, so this dark structure, it is still pure cadmium, and the lighter structure, it is still bismuth pure. Kalau you check under special equipment, we can point at this and do analysis. This they will produce the output will tell you that this one is bismuth. Okay, you can see the data that produced. They give a peak. This peak consistent to bismuth, for example. Okay, by using X-ray. Okay, X-ray can identify this as pure bismuth. If it is an alloy, for example, bismuth plus copper, maybe this peak is not present. Okay, it will be somewhere here. Okay, it will be somewhere here that indicates bismuth plus copper, for example. So there's no peak here, so meaning that it is not pure bismuth. It is bismuth plus copper. However, if you check this under the what is an example of an instrument? Energy dispersed X-ray. Okay, we have this kind of equipment in mechanical, in UTM, a lot in UTM. Okay, so this equipment can tell you if you point here, it can tell you what kind of the element. If you point here, it can tell you what is the element. So you can see that under this kind of analysis, whether or not you can obtain alloy as a insolubility alloy phenomena. Right. The phase diagram. Okay, the term phase is used to refer to a physically homogeneous state of matter where the phase has a certain chemical composition. Okay. The phase present in an alloy depends on the alloy composition and the thermal treatment to which the alloy has been exposed. Okay. So meaning there are some information about composition and the heat. Okay, the temperature. So when alloy solidify, the system has two different temperature range where solidification happens. Okay, so last time we talked about alloy. This for the pure metal. In topic 3, pure metal. Okay, for pure metal, when you solidify the liquid reaching the freezing point or melting temperature, okay, there is a horizontal line for the curve and reduce the temperature when it completely forming a solid. Okay, so this horizontal line will not be observed for the alloy. What you can see a gradient of temperature. Or sometimes you may see some in the notes having this kind of gradient temperature. Okay, whatsoever, but there is a two limits. Okay, so T liquid means that above this temperature it is completely liquid. T S limit is a limit where 100% solid will obtain or completely solidify. This is a limit where you achieve during the cooling process a complete solidification process. Okay. So the construction of phase diagram is by plotting the variation of temperature and the phase transformation during the heating or cooling of an alloy system of various composition under equilibrium condition. Equilibrium is you allow the reaction at okay, non-equilibrium when you force it to form a certain phase. Equilibrium is when we do it cooling process, we allow diffusion happen slowly. For example, we do a cooling process at a very slow cooling rate. Then you can obtain the equilibrium condition. Okay, but if it is not equilibrium condition, it will for example, you do it a very fast cooling. Okay, at that time you will obtain non-equilibrium phase, where over the time there's so much residual stress inside the phase, and over the time it will age or change its phase. Okay, that one is non-equilibrium. But when we talk about equilibrium, we let the diffusion occur smoothly, and it will stable at that condition over the time. Okay, so to obtain this equilibrium condition, you need to cool it naturally. Okay, and naturally without forcing it to cool very fast. Okay, if you force it cool very fast, meaning that within a short time, it won't be equilibrium. Okay, you may see this example in chapter 7. Okay, during heat treatment process. So at that point, maybe you can see the example and understand the phenomena. Okay, so to allow it a stable condition, we let it cool naturally. So we heat it, for example, this is how they construct the phase diagram. Okay, they combine between A and B. Okay, A and B elements. So inside A, you add B element, okay, to construct, to obtain one complete alloy system. For example, you want to mix between A and B. You want to see where is the limit, okay, either the temperature and the composition. Okay, remember when we talk about phase diagram, it's involved temperature and composition. Okay, so for the alloy, when you mix alloy, zero element, zero B concentration. You can see the horizontal line. Okay, this is melting temperature of A, because there's no B, right? This is element A. Okay, melting temperature. So 0% B, this is percentage of B. Look at this, 0% of B. Okay, so what the cooling curve, this is cooling curve. Okay, so the cooling curve will show the behavior of pure metal cooling curve. Okay, this is belong to metal A. And then if 100% B means it is pure metal B. Okay, in between there are a portion of B inside A. Okay, so at first they investigate the cooling behavior, the cooling curve for the 10% alloy elements of B inside the parent elements of A. Okay, this is a solvent. At this point, A is solvent. Okay, B is solid atoms. Okay, so for first testing 10% elements B, and they obtain this gradient temperature during transition between solid and liquid. Okay, so what happened at this green line is the mixture between solid and liquid. Okay, inside here there's a solid and liquid. Solid plus liquid. Okay, remember? Okay, at this point there are solid plus liquid, where at this gradient temperature. Okay, so this one is liquid. This one is solid. So during this between 0.1 and 0.2, it is solid plus liquid. So, okay, at this range, what you get is a phase, combination phase between solid and liquid. So the red region is a liquid region. And what about the blue one? Okay, this area, blue area, what phases?
Solid.
Solid. What kind of solid? What kind of solid? Is it element A or B?
Element
Solid solution.
Element B.
Element B.
A and B.
A and B. A and B. Okay. Or we give a name which is phase alpha, for example. Okay, new phase. Okay, irregular. Remember? Irregular. A and B. All right. So that's good. So new phase. So by removing the time axis from the curve and replacing it with the composition, the cooling curve indicates the temperature of the solidus and liquidus for the given composition, like this. Okay, like this, right? So the temperature, gradient temperature 1 and temperature 2. Remember, this one is T1 and T2. Okay, so T1 and T2, where we get T1 and T2, for example, this is 10%. So, oh, sorry. Okay. Right. For example, the 10% B. Okay. We obtain this kind of gradient temperature, T1, T2. Just record temperature, remove the time. Remove the time. Okay. To construct, this is how we construct the phase diagram. How we construct the phase diagram. Okay. So temperature versus composition. We remove the time. So there is a temperature 1 and temperature 2. So we just record temperature 1 and 2. And same goes to the 20% of element 3. Temperature 1, temperature 2. And same goes to 30%, 40%, 50% until we got 90% and 100%. This 100% is melting temperature of element B. This one is melting temperature of elements A. So now we got phase diagram. What is phase diagram? Is a diagram for the temperature versus composition of two elements. Okay, this is binary phase diagram lah. Binary means there are two elements. Okay, if you add A plus B plus C, so we have another system, ternary phase diagram. So now we discuss about binary. Binary. Okay, so each phase within an alloy has its own distinct physical, mechanical, electrical, and electrochemical properties. Look at this, each phases. Okay, kalau dalam ni you dapat phase, for example, this is liquid phase lah. You mixkan between A and B di dalam bentuk liquid. This one is solid. Okay, we name it, for example, alpha. So this one you have ni L lah, liquid. L plus alpha, solid alpha. Okay, so the line, a red line, we call it liquidus line. Why? It is a line where the point where it's transformed from completely transformed into liquid. Okay, ataupun or during the solidification, this line indicates the point where solid will begin. Okay, solid will start to form. Okay, let's say you have 75% of elements B. This is the temperature where you can find for the beginning of solidification. So meaning that if you want to turn it into solid, make sure the temperature is beyond this limit. So now you can find any point. For example, you want to search for the 92% of elements B. So you can find it here. You can use it for any alloy composition. Okay, this is how they construct the phase diagram. So now, just now we have alpha. So this phase, okay, the solid solution phase, that just now is only one example of phase. If there are more than one phase, okay, so each phase having their own physical, mechanical, electrical, and electrochemical properties. So if you want to design an alloy, you have to make sure what kind of properties you want. Okay, let's say it has a phase alpha, phase beta. Okay, this property, for example, ductile, okay, tough. This one is brittle, hard. Okay, so if you want to design a material that having high ductility or toughness, you have to ensure that this element is limited. Okay, you need to design this element. If there is a beta element inside your alloy, you have to design it so that it won't easily fracture. Okay, you need to restructure it so that, or maybe if you want to making an alloy, you have to ensure that your alloy doesn't consist of this kind of pieces. Okay, you add A and B, it will produce alpha and beta. So how many beta, how many elements B need to be added? So you will, so that you can add more alpha. Okay, so you change this, you will change the presence of phases. Okay, so because alpha and beta will have a different properties, so you have to know if you want to add, you want to make or choose an alloy, so make sure that what kind of phases. Okay, you cannot just simply, oh, kalau aku tambah carbon dalam besi ni, maksudnya besi aku akan jadi kuat. No, not like that. So you have to ensure how many percent of carbon need to be added in your alloy, so that it will produce the desired properties for your design. Okay, phase diagram provide information on melting, casting, recrystallization of alloy. Okay, melting apa tadi saya cakap? I have mentioned about the temperature where you can transform your alloy into liquid. Okay, just now there is a limit like this, temperature versus composition. Okay, this is liquid, this is alpha plus liquid, this is alpha. All right, so the phase diagram provide information on melting. Okay, so this is melting point. Whatever the alloy, for example, this is 10% of element B. This is melting point. You have 90%. This is melting point. If you have 50%, this is melting point. Okay, that's information that can be obtained from the phase diagram. Okay, so casting. If you know the melting point, you know what is information needed for the casting process. Okay, recrystallization. Okay, at what temperature recrystallization may occur? Okay, if you want to do the aniline process, okay, you allow the phenomena for recrystallization. What temperature for the aniline process? Apa dia? Aniline temperature? Anyone? Apa dia?
55.
I cannot hear you. What is the temperature for aniline?
55.
What is 55?
55 degrees Celsius.
55. Where do you get 55?
Google.
Google search. Okay. What is
Yes.
the What kind of materials is that?
Wait.
Apa bahan itu yang 55% tu? 55 degree Celsius tu?
Says here of a standard PCR protocol.
Apa dia?
Well,
What kind of material is that?
not
Do you
stated,
know what
doctor.
is the
Uh,
material for the 55 degrees Celsius?
handling
Or you
temperature.
can use 55 degrees Celsius for any material. For example,
No.
I want to do an handling process for aluminum, I need to use 55 degrees Celsius. And then if I want to use an handling process on the steel, I can use temperature 55 degrees Celsius. Is that what you mean?
No.
No. So what is this?
Handling temperature is slightly lower than melting temperature.
Yes, slightly lower. Not slightly lower. It is lower, but how much it is lower?
Standard is 3 to 5 degrees Celsius lower.
So almost melting.
Yes.
Almost melting. Okay. So
3
you
to
can do
6
handling at
degree
that
low.
temperature. What? Apa dia? Macam ada bunyi tadi. Give me the correct answer. So at least you know the 55 degree is not the analytic temperature. It may be analytic temperature for some materials, but not for all. Okay, now you know. It's not one single temperature for the analytic process. And if analytic process temperature depends on the material. Okay, now you know that. Okay, what else information? How to determine the analytic temperature of any materials? Anyone? Tak ada?
A few degrees lower.
50 degrees lower.
A few.
A few degrees lower.
Yes, 3 to
Okay,
6.
few degrees lower. It is lower, but not few degrees. There are some methods to identify it. Where do you learn about annealing process?
Chapter 3.
Chapter 3. For what? Why we do annealing process?
Crystal growth. Crystallization.
Crystal growth. Yeah, for crystallization. That's good. Why we want to recrystallize our materials?
To form a perfect crystal structure.
Okay, why we want a perfect? Our crystal structure is not perfect. That's the reason we want to make it perfect. Why?
A stronger crystal, a more tersusun crystal structure tu lagi kuat material.
What happened to the current structure that you want to make it more tersusun?
Dia ada lompong-lompong dia, so kita add alloy ke apa ke dalam tu.
Okay, all right, that's your answer, but not really accurate. Okay, do you know why we conduct annealing process? No answer for that. Okay, let's take a break for 10 minutes. Okay, come back later at 4:06 and give me the correct answer for that question. What is the annealing temperature? Okay, all right. So take a break 10 minutes.
Yang item baru.
0.4 of melting temperature.
Yes, exactly. It is about between 0.3 and 0.4 of melting temperature. If your materials have a melting temperature at 700 degrees Celsius, so it is 0.3 or 0.4. It is about 0.4, but the range is between 0.3 and 0.4. And 0.4 melting temperature in Kelvin. In Kelvin. So you need to convert it into Kelvin, degree Kelvin, and take 0.4 out of it. Okay. So it is 0.4 melting temperature in Kelvin. All right. So it is an okay. Next week exam kan, test kan. So the test during the next week. So annealing for the recrystallization of the code work. Okay, code work, deformation after code working process. There are changes in the material properties. We do annealing process for revert back the original materials properties. Okay, so remember this. Okay, so you want to do crystallization, so you have a whatever the element composition that you want. Okay, you know the melting temperature. Okay, melting temperature where it start to form liquid, right? So just now I mentioned about melting temperature. This is not melting temperature. It is the temperature where completely transform into liquid. We call it liquidus line. And solidus line is the temperature where it starts to form liquid upon heating. So you have at room temperature, you heat it up, approaching this temperature, it starts to form liquid. So 1/3 over this temperature, okay, 1/3 of this melting temperature or temperature where it begins to form liquid. So 1/3 of it, you can get recrystallization behavior of the alloy. So now we talk about alloy, not pure metal. So from the alloy, from the phase diagram, the information of this alloy we can obtain such as melting, casting, recrystallization of the alloy. Okay, for a specific temperature and composition, phase diagram reveal the information such as the number of phases. Okay, just now we talk about alloy in general, but for that particular alloy, okay, for example, you have alloy, okay, plumbum plus a sternum, okay, plus sternum, and inside this you have how much? Let me give 40% plumbum, 60% sternum, okay. So for this alloy, okay, specific temperature and composition. At specific temperature, let's say you set temperature at 200 degrees Celsius, okay, you can get this information. One, the number of phases present, okay, the composition of each phase. Okay, let's say you dapat phase alpha plus beta. For example, there are two phases at this particular temperature. What temperature? 200. What alloy? This alloy. Okay, the alloy that contains 60% sternum and 40% plumbum. Temperature 200. What you get? The type of phases, the number of phases. Okay, number of phases. Maybe 2, maybe 3. Okay. And then what else? The composition each phases. For example, this beta, this alpha, you can get what is it? You can determine the composition. Okay, for example, we have two phases, alpha and beta. You can determine the composition. What composition? Composition, for example, in beta, at this temperature, it's contain 70% sternum and 30% plumbum. Okay, and for this temperature, if you have this alloy, at this point, you can determine for this alpha, maybe it's contain 10% sternum and 90% plumber. Okay, this kind of information you can have. Okay, and it is useful for a certain purpose. Okay, of course you don't have to know what purpose, but basically we can do it by a true phase diagram. Okay, the percentage of each phase diagram. Apa pula ni? Okay, so meaning that let's say in this condition um, you have alpha and beta, right? So at this point, how many percent beta and how the portion, the fraction, okay? For example, at this 200 degrees Celsius, apa benda ni? Okay, for example, at 200 degrees Celsius, for your alloy containing plumber plus 60% stannum, okay, 40%, and this is your alloy, this is temperature. You want to know if there is alpha and beta, how many percent alpha and how many percent beta, okay? So total, of course, 100% of the alloy. So now the percentage each phase. Okay, for example, at this temperature, you can determine, for example, you get 70% is alpha, 30% is beta. Okay, we can do it, all right? So I'll teach you how to determine later in the next lesson. So in short, okay, alloying elements are added into host metal, which is a pure metal, to alter its property. Okay, the pure metal is not having the complete best properties. Okay, but if you add another elements, you can improve a certain weakness of the pure metal. We define solubility limit as the maximum equilibrium concentration of solute in a host materials, and solubility limit is dependent with temperature. Macam air gula kan, like a sugar water, if you increase temperature, you can add more sugar. Okay, due to the solubility limit, different type of alloy can be formed. Okay, this alloy consists of different phases, which in turn give them different properties. Phase diagrams are valuable resource in predicting behavior of alloy during solidification and the microstructure which will be produced. Okay, remember, at a certain temperature, we can predict how many percent alpha, how many percent beta, and we should know what is properties of each phases. Let's say this is ductile, this is brittle. Okay, at certain temperature, you can have more percentage of alpha, meaning that at certain temperature, the total properties of your alloy may change. Okay, so that's the information which is very valuable resource in order to us to make an action when we do analysis on the process. Okay, right, moving on to the next lesson, lesson 2. Right. So this is binary phase diagram, isomorphous system. Okay. You need to understand the isomorphous phase diagram system, how to construct and read the phase diagram, and understand how non-equilibrium cooling causes crystal segregation. Right. The binary phase diagram are like maps that present the relationship between temperature and the composition. And in fact, you can quantify the phases, okay, at equilibrium, which influence the microstructure of an alloy. Okay, binary phase diagram are helpful in predicting phase transformation and the final microstructure form. Okay, isomorphous system is referred to the metal that are completely miscible in each other in both the liquid and solid states. In isomorphous system, the two components have unlimited solubility. Okay, This is example like when you add alcohol in the water, or you mix between alcohol and water, you can have 99.99% alcohol, or you can have 1% alcohol in 99% water. So alcohol and water is miscible. Okay, forming one isomorphous system. Okay, this is a complete solubility, actually isomorphous. Okay, complete solubility, similar to complete solubility. Okay, I have explained this earlier. All right, this is example when you mix between nickel and copper. So this is 0% nickel, this is 100% nickel. At the top x-axis, and the bottom x-axis is referred to 100% of pure copper and 0% copper. So if you read from the left to the right, what is percentage of element? So it is increase of percentage of element what? If you read it from left to the right, increasing in the elements, percentage of elements, nickel. Okay, so this is 100% copper means 0% nickel. 80% copper means 20% nickel. Look at this. This is 20% nickel. All right. 60% copper means 40% nickel. Okay. Right. Okay. So let's say you have 100% copper. So this position, this point, okay, vertical line, yang kosong ni, 0% nickel, which is 0% nickel means 100% copper, right? So this point, it has only one freezing temperature or melting temperature. It is horizontal line. So only one single temperature. It is about 1000 degrees Celsius. And when you add 20% nickel, what happens is you can see two different temperature during the transformation between liquid and solid. Remember, okay, before this point, this curve is actually temperature versus time. Okay, during the cooling process, it is a cooling curve. Cooling curve. Okay, so this is a cooling curve. This is a cooling curve for the 20% nickel in 80% alloy. So when you construct the phase diagram for this isomorphous system, okay, there are two temperature here. Okay, you just recorded the two temperature, which is one is at 1200, one is 1150. Okay, this cooling curve is belong to the blue cooling curve belong to the 60% copper and 40% nickel, and the purple is here, and the green one is here, and the 100% is here. Okay, which is about 1450. Okay, this line, we call it liquidus line. Okay, this one blue line is solidus line. Okay, so the region, this region above the red line is a liquid. Okay, so this point, okay, the region below the blue line is a solid, and the between is liquid and solid. Okay, so how we construct the red and blue? Okay, this is temperature 1 and temperature 2. Okay, it is temperature 1 here, temperature 2 here. And then let's say this is temperature 3 and temperature 4. This is temperature 3, temperature 4. Okay, we label, we mark here, and then we construct a continuous line, okay, connecting all the first top line, this top line. Okay, and this melting temperature, the melting temperature of nickel. Why nickel? Because this is 100% nickel. So at this line is 100% nickel. At this line is 100% copper. Do you get it? Hello?
Yes, doctor.
Yes, doctor.
I thought that I have logged out from the meeting. Okay. So now you can construct a line, namely liquidus and solidus. So this phase diagram, you can use it to design any alloy. For example, 50% copper, you can search information for any alloy. Let's say 88% copper, right? So this is how they construct a phase diagram. Okay. So let's say you want to analyze about the alloy containing 50% nickel and 50% copper. So you know that at this point it is a completely solid, and the bottom region is a completely solid. So what does it mean? So let's say this is your alloy. Okay, you want to you prepare the alloy. Okay, it is liquid. The temperature above this point is liquid. So what temperature that the nucleus start to form? Nucleus start to form is a beginning of solidification, right? So at this point, okay, about 1,300 degrees Celsius or 1,320 lah, okay, for example. At this point, solid will start to form, okay. If you want to prepare to make it completely liquid, make sure the temperature above this limit, okay. And when it will start to form solid, when the temperature reduce to 1,320, and when it continuously reduce, the portion of solid become larger and larger, it will grow until completely become 100% solid. Okay, so crystallization will end here at this point. Okay, now you can now you understand. Oh, at this for example 1,270, you can degrees Celsius, you can ensure it is completely 100% solid. Okay, there will be no more liquid in your cast material. So in between, okay, in between there are liquid and solid phase. Okay, in equilibrium. All right. Okay. What are the phases exist at 1,200 degrees Celsius for this alloy? What alloy? The 50% nickel. So it will be liquid and solid. Yes. Okay. What are the phases? Liquid and solid. What is the composition? Okay. But this is how you can determine the composition. Okay. At this point, you take a horizontal line connecting between green, crossing green and blue line. Okay. You construct this line. You call it level rule. Okay. Until it's crossing, intercept. The intercept, you can read from the intercept, you can read the composition. Remember this, the x-axis of this phase diagram is a composition. So the question asks you, what is the composition? Okay, of the liquid. Where is liquid? This liquid. So these are the composition of liquid. Okay, so this is composition of liquid. This is composition of solid, because this is solid, this is liquid. Solid is somewhere here, liquid is somewhere here. So we can determine the composition of liquid by constructing a horizontal line named level rule or tie line. Level rule. Level rule. Tie line. Okay, sorry. Tie line, level rule, to determine the fraction of phases. Okay, a tie line. Okay, and where is the composition of liquid? Here. This one. You can read it straight away from here. So it is about 50% copper and 40% nickel. So this one is 50%. It is increased in a percentage when you go to the left. Okay, So this is 50%. This is about 55.25%. Okay, this is of course very accurate data, but you can give an answer in the rough numbers, which is about 55 degrees percentage. Okay, if you have 55% of copper, so meaning that 100% minus 55%, okay, you can get 45% of nickel. So the composition of liquid equal to 55% of copper and 45% of nickel. This is how we write the composition. Okay, what is the composition of solid? What is composition of solid? Anyone?
What? Copper.
How much?
Uh, 43.75 copper.
43.75%
Copper.
copper. And what is the composition of nickel?
56.25%.
Okay, so you just read from here. Okay, this axis, this is about berapa ini? 33. This is 33. This is okay, fine. About that range. Okay. Of course, I answer. Right. So it is very simple. So meaning that you can draw a tie line and then look at the composition here at x-axis. Pasti x tu, baca saja. Okay, sangat simple. Right. Next is you can determine. Yes.
Again, how do you find the composition for solid?
What? I'm sorry.
How to find the composition for solid?
How to find the composition of solid? First, you draw a tie line. What is tie line? Okay. All right. The question asks you what to analyze. Do this analysis for this alloy. 50% copper and 50% nickel at temperature equal to 1300. So you draw a tie line at 1300. Okay. So now we want to know the composition of liquid. If the tie line crossing this point, this is composition of liquid. If the tie line crossing the blue line is a composition of solid. Why? Because the solid is located here, the liquid is located here. So this line crossing this point belong to the composition of liquid. You just straight away read from the bottom. Not 50%, in somewhere here. Okay, so if you look at this point, for liquid, composition of liquid, it is 55.25% of what? Copper. So nickel, you can obtain by reading on top of it. Okay, this point. Or it is 100% tola 55.25. Okay, you got this value. And what about solid? Solid, this tie line crossing this blue line, which is solidus line, and this value can straight away read at this point. Okay, this point. This point composition is 43.75% copper. Okay, so do you understand now?
Farm.
Okay, very good. So next is determining the phase fraction. So now we have at this point, this temperature again, 1300 degrees Celsius. At this point, you can determine the phase fraction. Again, what is phases at this point? It is liquid and solid. So now you have two phases. Please mute yourself. Solid, liquid. So we want to know at this point how many liquid remains in the casting material. For example, we did casting process. Okay, we want to know. Boleh tolong mute tak siapa yang on microphone itu? Kat masjid ke?
Dia ada mic terproblem.
Oh, ya ke? Siapnya.
Ah.
Alright. Okay. So two phases, we have solid and liquid at this temperature. Okay, our alloy 50% nickel, 50% copper at 1300 degrees Celsius. It has solid and liquid. So we want to know at this temperature how many solid already formed. Okay, how many solid remains? How many liquid remains in the cast material? We can calculate this. Okay, so composition of liquid and solid. This is composition. Okay, just now we have determined the composition. All right, we got this value. Okay, this is composition of liquid, this is composition of solid. So from this value, we can determine by adaptive level rule. Okay, so the length multiplied by the weight. We can having equilibrium if this multiplied by this equal to this multiplied by this. That's an equilibrium state. So to determine the fraction of M for S, we can take a fraction of this length over the total length, A plus B, multiplied by 100. Okay, you want to know what is the weight of this? This over the total length is equivalent to this multiplied by where this fraction is B divided by the total length. Okay, so then they will obtain the equilibrium state. So the MS, kalau S located here, so the fraction needed is A divided by total length, but liquid is here, so we take a B divided by total length. So now if we focus on this particular temperature, which is 1300 degrees Celsius, applying the level rule, so we can obtain the MS, the fraction of solid. Okay, fraction of solid. So solid is here at this section. Okay, so we want to know how many percent solid, so we take A over the total length, A over A plus B. Okay, so what is A? 50% minus 55.25. Okay, it is about ataupun macam ni MS equal to 55.25 minus 50 divided by total length. You can have it by 55.25 minus 43.75. Okay, so you can use directly the value for CL and CS. Okay, so just now I have shared with you this liquid and solid composition. So if we use only copper value, okay, ignoring this, okay, because it is a total will be 100%. So this one we can refer percentage of copper only. So how to get 5.25? It is 55.25 minus 50. This value minus this. You can get this length. Okay, panjang kosan tu. And then total length is 55.25 minus 43.75. Okay, or you can add between this and this. Okay, so you got this fraction. And also, if you want to determine the fraction of liquid, liquid is located here, somewhere here. So you take this length over the total length. Okay, 6.25 divided by total length, and you get 54.35, or ml also equal to 100% minus 45.65. Okay, 165. The total is 54.35%. Okay. So you can determine ml by 50 minus 43.75% copper divided by 55.25 minus 43.75% copper. So then you got 54.35% copper. You need to no, ni dah cancel kan, so tak ada lain copper ni, percent saja. Multiple by 100, so you got 54.35%. How do microstructure form? Okay, you can see the transformation. All right, this is a liquid. Liquid, if it's reduced in temperature, you will have one single phase which is liquid. But when it's approaching here, this point, what point is this? It is a point where nucleation begins. So what phase? Let's say this is alpha phase. Okay, this is liquid plus alpha. So nucleation of alpha will begin at this point. Okay, so it's contain 37.5% copper, the solid at this point. How do you get this? So by this point, this temperature, okay, you draw a line. Okay, you draw a line here. You get this is Cl, this is Cs. The Cs you can read here, it is about 37.5%. So solid percentage composition of solid, 37.5% copper. Without this, it is like a fraction of solid. With copper, if you write copper, this means composition of solid. When you write composition, you need to write percentage of what element. Okay, that's meant by composition. We know exactly how many percent of element inside the solid. Okay, all right. Your alloy containing 50% nickel, 50% copper. However, why this happened? Why it is 37.5% copper? In fact, our alloy containing 50% copper. Right? It is because of the diffusion phenomena. At this point, when nucleation begins, it reached in nickel. Okay, only 37.5% copper. Later, when you solidify 100%, what you got is, okay, if you draw a level rule here, okay, this is CS, this is CL. Okay, the liquid is if there's still an amount of liquid, the composition of liquid is about, I don't know, what is it, 35 or 60% or 65% of copper. Okay, but what about the solid? solid is 50%. So meaning that your alloy, when it is 100% solidified, it contains 50% copper. That's correct. Okay. So moving on to the next stage. Okay. When you reduce the temperature at a lower region, the alpha phase or the solid phase will grow. Okay, this is normal phenomena. We have discussed this in the chapter 3 during the solidification process. So meaning that in the liquid, there are nickel plus copper in liquid. Okay, at this point, what is concentration of the liquid? It is only contain only one single phase, which is liquid. So the composition is 50% nickel and 50% copper. But when there is a solid, okay, the composition is changed because the fusion of atoms for each element will change at this phase. Okay, when there is a solid at lower temperature, the solid will grow larger. Okay, and at this point, completely slightly lower than liquidus line, you will see that 100% solid. Okay, let's say we have a name of solid is alpha. So you can see the grain boundary form. Okay, how grain boundary form? When this grain is grow larger, they will meet at grain boundary. Okay, fully solidified. Okay, at this point, dapat jadi 43.7. It is supposed to 50% copper lah. Alright, copper nickel phase diagram. This is portion of the copper nickel phase diagram. Okay, at this point, T0. Okay, let's say we label it as T0. Okay, it is the first. Nucleation will occur. And upon reduction of temperature, the diffusion will occur around the nucleus. Okay, this is temperature 2. We draw a tie line. It will show a different composition of nickel. T3, at this region, it will form another composition of nickel. And until at the end of this point. Okay, so it because of the non-equilibrium cooling process. Okay, so for the phase diagram with equilibrium cooling process, you will see an uniform crystal structure of the solid alpha. Okay, crystal segregation. Monel, this is a microstructure of monel in the dendritic microstructure due to rapid cooling rate. This is monel heat treated at homogenized from this structure, which is non-equilibrium. It will homogenize if we do a heat treatment at 171 degrees Celsius for 12 hours. Okay, and heat treated to homogenize at different temperature, we get a different composition, but still it has a light color and dark color. Okay, it's contain two different phases, so we can modify by induced temperature and time to modify this plate-like structure into what we call it precipitates. Okay, so the mechanical properties will change over the composition of the alloy. For example, copper and nickel. This is copper and nickel alloy. If you add nickel in copper, you can increase. Okay, pure copper is very soft, but if you add nickel, you can increase at maximum. But the tensile strength will reduce if you put too much nickel. Okay, compared to pure nickel and pure copper, pure nickel has higher tensile strength. Okay, but if you mix between these two, you can achieve higher performance of tensile strength. However, ductility will decrease at maximum 60%, okay, of nickel. So isomorphous diagrams are those for which there is a complete solubility, okay, complete solubility. Pooling curve are used to construct phase diagram. Thailand is used to determine composition of phases. Lever rule is used to determine phase fraction. Microstructure of metal can be predicted from the phase diagram. Okay, crystal segregation are differences in the chemical composition within a grain, and crystal segregation could be avoided by sufficient slow cooling. Okay, slow cooling is a method to achieve equilibrium structure. Basically, phase diagram, we construct phase diagram by using an equilibrium phases, meaning that we conduct slow cooling, as resulting differences in concentration can always be compensated by diffusion process. So mechanical properties of alloy are dependent on the composition. Okay, I think that's all for today. Any question before we end our meeting for today?
How about attendance?
Lah, saya lupa lah. Aduh. Sekejap Kelas ke lepas ni?